At the end of this lecture, you should have a good idea of what are some of the decisions that you need to make while training a machine learning model. These decisions will affect the parameters that you use during the training process. In this lecture, we'll implement a model for multiple regression in TensorFlow. The code for this is very similar to linear regression. It's just an extension to allow more causatory variables. Linear regression can be thought of as representing a cause effect relationship between two variables. The cause is an independent variable and the effect is a dependent variable. One cause, one effect. For example, the movement of government bond yields affect oil prices. But it is often the case that an effect depends not just on one cause but on multiple causes. Your independent variables can be more than one, and the effect is one dependent variable. Modeling this is a multiple regression problem. For example, the returns of ExxonMobil depends not only on the Nasdaq share index but also on how oil prices change. Many causes, one effect. You'll find that the steps for multiple regression are very similar to those that we followed for linear regression. You should be able to find exact comparisons. We'll set up our multiple regression model using a different data set which requires a different helper function. Read exom oil NASDAQ data. The return value of this function is a tuple with three fields: returns for NASDAQ, oil, and exom. As before, each of the returns is represented as a one-dimensional array. The read file function, which reads in data for our multiple regression, is a little different. We still read in CSV files for NASDAQ, oil, and ExxonMobil. We access the date and the adjusted close in each of these files, sort the data frame by date, and find the percentage change or the returns. At the end of this helper function, we return the NASDAQ data, oil data, and the exom data, a tuple with three fields representing returns. As before, we'll set up a baseline implementation for multiple regression using Python's scikit-learn library. The next step is to get the returns for NASDAQ, oil, as well as exom using the helper function that we just set up. First step is to combine our regressors, the two causatory variables of our multiple regression, NASDAQ data as well as oil data. If you remember, when you use Python libraries for regression, you have to set up the data the way the library expects the data to be, which means our x variables should be arrays of arrays. Because we are working on both NASDAQ and oil data arrays, we achieve this by using the vstack function. Vstack stacks arrays vertically to make a single array of arrays. After performing the vstack operation, we take the transpose of the result. This will give us data in the format that we require to run multiple regression using these Python libraries. Set up a linear regression model to represent this. Fit this model to our combined regressors, that is NASDAQ returns as well as oil returns, and exom data is our dependent variable. You can compute a score for the resultant model. This is the R square, a measure of the goodness of fit of this model. This is a slightly different measure than we've been working with, so let's ignore that for now. And we can finally print out the coefficient and intercept of our regression. The one difference here is that because this is multiple regression, you'll have two coefficients and one intercept. Execute this bit of code, and here are the weights and biases for this model. We have two weight variables, one for NASDAQ and one for the oil data, and one bias variable. Let's now set up a multiple regression model using TensorFlow. You'll find that the code for this is very similar to our linear regression code, except that you have to take into account an additional x variable. Each of these x variables have their own weight variables that we have to calculate. So we set up the NASDAQ W and the oil W as variables. Initialize them both to zeros just like we did before, and also notice their shape. They are arrays of arrays with just one element in each dimension. Set up a variable for the bias B and initialize that to 0 as well. We need two placeholders to feed in our two x variables. our returns for NASDAQ as well as oil prices. Notice the shape of these placeholders. They're the same as we saw before. The first dimension is none or unspecified because we don't know how many data points we'll be feeding in. And the second dimension is 1. We perform two intermediate computations. We multiply NASDAQ X by its corresponding weight, and we do the same thing with oil X. These are both matrix multiplication operations. We can now calculate the predicted value of y by fitting that linear equation. Y is equal to NASDAQ WX plus oil WX plus B. We need to feed in labels for our training data set, the actual y values that correspond to the x data that we fed in. We use a placeholder to hold this data. We call it y underscore as before. And once again, its shape is none comma 1. We don't know how many data points we're going to feed in, but each data point has a dimension of 1. The cost function is calculated in an identical manner. Perform the reduce mean computation on the squares of the differences between the actual and predicted values. We set up an optimizer to minimize this cost function. We use the FTRL optimizer as we did before. You are, of course, free to choose other optimizers such as the gradient descent optimizer or the Adagrad optimizer. We reshape all our NumPy arrays so that they are in the form that the model expects. If you remember, a reshape of -1, 1 converts a single dimensional array to an array of arrays, where the inner array has just one element in every array. Store the length of the entire dataset in a Python variable, and now we're ready to look at our function, train with multiple points per epoch. The arguments to this function, steps, train step, and batch size, form the three parameters that we can change within our training model. For any machine learning model that you have to set up, these are three decisions that you need to make: the number of epochs or steps that you'll use to train your model, what optimizer you'll use to minimize your cost function, and finally, what is the size of data that you'll feed in every epoch, the batch size. For the training of any machine learning model, these are some of the properties that you can tweak to see if your result improves. A whole block of code here is exactly the same as we saw in linear regression. We initialize all the variables using the global variables initializer. We instantiate a session. We set up a for loop which runs the training model on a batch of data multiple times. The number of times is equal to the number of epochs. And we identify the start index and the end index of the batch of data that we are going to feed in every epoch. In order to run the training step of our regression model, we need to feed in three pieces of information. The feed dictionary has to have the X values for NASDAQ, oil, and our Y labels for exom. Once we've set up the feed dictionary, we can call session.run on our optimizer, and we print some data to screen for every 500 iterations. This will help us see how the model converges. Go ahead and call train with multiple points per epoch for 5000 epoch, pass in our optimizer, that is the train step FTRL, and use the entire dataset size as our batch size. And at the end of 5000 steps, you can see that our weight values W1 and W2 are very close to the baseline that we had calculated earlier, as is our bias value. Scroll back up and a quick comparison will show you that this is true. Some of the decisions that you need to make in the training stage of your machine learning model is: how many epochs will you run this for? What is the optimizer function that you'll use? And finally, what is your batch size? Tweaking all of these will give you different results, and you need to find the one that works best for you.